Good afternoon. In this poster, I will talk about dynamics of episodic magma injection and migration at Yellowstone caldera constrained with InSAR and GPS data. As some of you know, rhyolitic magmas are responsible for the largest and most explosive eruptions on Earth, which result in the formation of large collapsed calderas like Long Valley and Yellowstone. Some of these calderas remain restless for several thousands of years after their formation, and they tend to show transient pulses of ground deformation whose driving mechanism is a matter of controversy to date because a lot of these volcanoes have large hydrothermal systems. In this poster I have two research questions. What mechanisms do produce ground deformation at Yellowstone caldera, shown on the right in the western United States? And if the deformation is of magmatic origin, what is the eruptive potential of these pulses of magma injection? To do so, I will use legacy MVSAT data acquired more than 15 years ago. Despite the relatively large amount of usable SAR images, previous studies have only used very limited amounts of data, as shown in this table. In general, the data quality is regular because of the vegetation conditions of the volcano, but some interferograms, like this one on the right from Chang et al., are quite good. Unfortunately, InSAR is not usable in the winter at this volcano. Therefore, these old MVSAT data sets can be reanalyzed with modern tools like the NSVAS InSAR software to better understand the process of potential magma migration and injection at the caldera. This figure shows four maps of total ground deformation recorded by four different MVSAT tracks. Despite the variable coherence, all of them show the same signal: 25 centimeters of mostly uplift at the Sago Creek Dome, 20 centimeters of mostly uplift at the Mallard Lake Dome, and 8 centimeters of subsidence at the Norris Geyser Basin. The data, shown on the left column, can be modeled by a combination of one pressurized seal below the caldera and one depressurized seal below part of the caldera and Norris Geyser Basin. The depth of and the volume changes of these sources are shown in this table. If the uplift at the caldera results from magma injection, the maximum overpressure that can explain that can predict the observed ground deformation is not large enough to trigger a dike intrusion and an eruption in this volcano. To answer that question, I will use a GPS time series shown in here, because the InSAR time series shown on the right for the points of the same color on the lower left, lower right figure panels do not have the temporal resolution to properly track the caldera uplift. However, at least for the Norris Geyser Basin shown in here, they do have the right temporal resolution to track the subsidence until mid-2008. I use a combination of a free GPS time series from this station shown on the lower left with a fluid and solid mechanics model in which magma ascends by its overpressure from a deep mantle source towards a shallow pressurized reservoir. The vertical components of the GPS time series have been normalized by their maximum, and the red line shows the synthetics predicted by the best fit magma injection model, in which the pressure in the deep mantle source is shown on the green line, and which increases linearly until it reaches a threshold for the rest of the period of injection. This indicates that the data are consistent with a model of magma injection, and that drives the caldera uplift. I conclude that in the Sentinel-1 era there is value revisiting these old MVSAT datasets to assess the source geometry, but unfortunately the old MVSAT time series do not have the temporal resolution to track dynamic processes. We have to rely on GPS to state that magma injection is the most likely mechanism responsible for the caldera uplift during the period of interest. Also, there is no evidence for future eruption that can occur at Yellowstone caldera, at least on the short timescales of this study. Thank you for your attention.